So we looked at discrete probability distributions, and we looked at the specific case of a binomial distribution. And we saw that if x is distributed as a binomial with parameters n and p, the probability that the random variable takes on a specific x value is given by this binomial probability formula. It comes from the binomial expansion. But what happens as we let the number of trials get infinitely large? What happens as n goes to infinity? Well, this is beyond the scope of this course, but what we see happen is that this is equal to e to the negative m times m to the x over x factorial, where x can be 0, 1, 2, da 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 da. X would still be the number of successes in this problem, and m is some parameter that we're dealing with. And this, ladies and gentlemen, is what we call the Poisson distribution. We say that if this thing is one of these Poisson distributions, x is distributed as PO parenthesis m. It's distributed as a Poisson distribution with parameter m, and it so happens that m, that parameter, is the same as the mean, and it's the same as the variance. And that's nice for us because to get mean and variance, we don't actually have to do any calculations. We just have to know what the parameter is in this distribution. So what makes something Poisson? Well, there are three conditions. The occurrence of an event at a particular point in space or time is independent of what happens elsewhere. So if I'm looking at one stretch of time, the probability of that event happening has to be the same as in another stretch of time. The probability of an event occurring, that two events will occur at precisely the same moment. And some examples of this we see right here. Examples are number of phone calls received during a given period of time, or the number of accidents during a given period of time, the number of typing errors on a randomly chosen page of a book, the number of flowers in a randomly chosen area of a field. So you can see that these probabilities are over a fixed region or a fixed amount of time, and that's the clue that it's going to be a Poisson distribution. So let's get into examples. So in this example, our variable x is distributed as a Poisson variable with a parameter of 2. I want to know what the probability that x equals x for each of these possible x's are, 0 through 5. So the probability that x equals 0, we use our Poisson distribution formula. So it's going to be e to the negative second times 2 to the x, so 2 to the 0 over 0 factorial. Remember, anything to the 0 power is 1, as is 0 factorial. So this becomes equal to e to the negative 2, and we can put that into our calculator. The probability that x equals 1 success, we would have e to the negative 2 again, e to the negative m, the parameter, times the parameter to the number of successes over the number of successes factorial. So we get 2e to the negative 2, and we can put that in our calculator. And what you see here is we have to use our calculator for this. So let's just use our calculator from the get-go. I'm going to grab a list and spreadsheet page, and in this column I'm going to put my x values. And then in column B, I'm going to go up to this header row. I'm going to put equals, and we're going to menu. Statistics, distributions, and down here at the bottom, you see Poisson PDF. I picked that. Lambda for this problem. The parameter, m, lambda, whatever it's being called, that's the parameter, 2. And then for this particular thing, I don't want to put in a specific x value. I want to generate a list of all of my x values that I'm looking for, and I put those into column A. So I'm going to press Shift and A, press OK, I rhyme nice. Enter, and there we go. Here's our probability of 1 success, 2 success, 3 success, 4 success. And if we go down to the bottom, guess what we'll find? Probability of 5 successes. Now here's a question. What's the biggest x can be? Well, the biggest that x can be is, there isn't a limit. X could be as big as we want it to be, but these probabilities will get smaller. Remember, the mean number, the expected value, is 2 in this problem. So the further away we get from that, should make sense that the chances of that happening are going to get significantly smaller. If we look at a graph of this, we can sort of see what happens. And what I'm going to do is I'm going to assign labels here. We'll call this one R just for fun. And we'll call my probabilities, we'll call that P. I'm just picking letters. I'm going to add a new page, and I'm going to add data and statistics. And down here we want our R values, we want P going up this way, and you can see that it starts out with a peak, and then it comes down here and starts to taper and gets closer and closer and closer to 0. And you're going to see problems where you have to create one of these, usually as a histogram. So let's go into our menu, change the plot type. I thought it would let me make a histogram. I guess not, but we could draw a bar going up to each one of these dots. Of course, this is a bar graph, not a histogram. It's not continuous data. These bars should be centered above 0, 1, 2, and going up to those values, not touching. Okay, so away from the calculator and into another example. X is distributed as a Poisson variable with some parameter, some mean m, and I'm told the probability that x equals 0 is 0.2. I want to find m, I want to find the mean, and I want to calculate the probability that x is less than or equal to 4. All right, well, how do we do that? Oh my goodness, I don't know m, what do I, we're going to write an equation. Fear not, people, it's okay. So we're going to have e to the negative m times m to the 0 over 0 factorial. This equals 0.2, they tell us. Well, m to the 0 is just 1, as is 0 factorial, so we get e to the negative m equals 0.2. We know how to solve an equation like this with natural logs. Negative m equals natural log of 0.2, so m is equal to the opposite of natural log 0.2, and this is something that we can get from our calculator. Yes? Yes. And what we get is approximately, we don't know exactly what this is, but we find that this is approximately 1.61. If it asks for the exact value, we'd be giving this. If it asks for the approximate value, we'd get that. Now, find the probability that x is less than or equal to 4. So we could make a table. Values of x, probability that x equals x, and start with 0, 1, 2, 3, 4, and find all these probabilities over here. But remember, we saw in the calculator that we can do a probability cumulative density function. So let's go over to our calculator and see if that same capability is here. So I'm going to go menu, probability distributions, and down here at the bottom, Poisson CDF. That's beautiful. So, what was lambda? I don't want to use a rounded off lambda. So what we typed in was negative natural log, stay with me here, of 0.2. Now, let's take this and store it as, let's store it as m. That's what we solved for. Now anytime I type m, I'm going to use this nice long decimal, not just the itty-bitty rounded off one that I wrote down on my exam paper. So back into probability distributions. Poisson CDF. Lambda is now m, lower bound is 0, and upper bound is 4. We press OK. Ta-da! Our probability is 0.976 to 3 significant figures. So we're almost done. 2 examples left. Here's another one similar to what we just had. X is distributed as a Poisson variable with parameter lambda. Find lambda given that the probability that x equals 1 is 0.25. Okay, same idea as last time. Let's see if we can't get through this. E to the negative lambda times lambda to the first over 1 factorial equals 0.25. E to the negative lambda, 1 factorial is 1 times, oh man, what do we do here? This isn't just take the natural log of both sides and get lambda by itself. We've got lambda 2 different places. Oh my gosh, the world is going to end, but relax. In the calculator, we can solve equations that are really icky and nasty, and that's going to be how we approach this problem. I'm going to go into my menu under Algebra, Numerical Solve. And what I'm going to type in is that equation that I just tried to solve. And that equation was e to the negative lambda. So e to the negative, I'll just use m here, except you already used m for a variable. I'll use c, I don't know, why not, times c equals 0.25. And now we have to put a comma and tell it to solve for c. And there we have it. There's our solution for c. 3 significant digits. It's 0.357. There's our parameter. That's the mean value. That's our parameter for the problem. And the last example has to do with an important property of binomial or of Poisson distributions. If x is a Poisson variable with parameter m and x is representing the number of successes on an interval of length L, the number of successes in an interval of length k times L is modeled by another Poisson variable with parameter k times m. So if the length of the interval is multiplied by 2, as is the parameter. So our example is that a book has 520 pages and 135 misprints. What is the mean number of misprints in this textbook? So, okay, mean equals 135 divided by 520, 0.2596, yada yada. So we would of course say 0.260. And if you don't believe me, here's what I typed in. So now part B says the probability that pages, we want the probability that pages 444 and 445 don't contain any misprints. So this parameter, x is distributed as a Poisson distribution with a parameter of 0.26. And that's the misprints per one page. Our new variable, we'll call it y, is distributed as a Poisson distribution as 2 times 0.26 because the interval is twice as long. You see how this is happening. My interval for the first random variable in part A, the 0.26, that was 1 page. I'm doubling my interval. So this is a Poisson distribution with parameter of what would that be, 0.52-ish? So to calculate this, so I go into probability, to distributions, down to Poisson. Lambda is going to be 2 times t. My my x value will be 0 because I want 0 misprints on the page. And we get that our probability is 0.595 to 3 significant digits. So there we go, bunch of examples, lots of calculator use. The calculator will definitely be your friend for this because this probability involves E. And involving E to get a real value other than giving it in terms of E, you need the calculator. Be comfortable with your calculator. Be happy with your calculator. It's a glorious and wonderful thing.